Hello friends, welcome to Truth of Physics. In this video, I will discuss on the solution of Laplace's equation. Okay, now the Laplace's equation, what is this? If you don't know how the Laplace's equation comes in electrostatics, then you can check out a video. The link of the video I will give in the description box in the I button. Now this is called the Laplace's equation. Del square V where V is the potential. Now this is the Laplace's equation. Now, you know that there are different expressions of the Laplacian, that is del square, right? Del square Laplacian operator in spherical polar coordinate, in cylindrical coordinate, and in Cartesian coordinate system. Now, for different coordinate systems, the solutions, the forms of the solutions will be different. Now, in this video, I will solve a problem that will help you to understand the solution of Laplace's equation in 1D in Cartesian coordinate system. Okay, now what is the and in the later videos I will make both the spherical the solution of Laplace's equation in spherical coordinate and in cylindrical coordinate also. So stay tuned, and if you are new, then subscribe this channel and hit the bell icon to get the notifications. Now in our today's video we'll deal with only Cartesian coordinate system. That is, in Cartesian coordinate system, del square V is equals to del square or d square V over dx square plus del square V del y square plus del square V del z square. Basically, if we take the v's out from every equation, then this is in the bracket represents that this is del square, that is Laplacian. Now this is equals to 0. Now in this case, suppose we have a problem given. Okay, we have a problem of electrostatics which states that we have like this figure, we have two plates, infinite extended plates, okay, conducting plates, which the upper plate is given potential is connected to a potential of 100 volt and the lower is grounded. Now and the middle region between these two plates is empty. That is, here in this place the rho, that is charge density, is equals to 0, and when the charge density is equals to 0, then you can easily understand that we have to use this, the Laplace's equation, del square V is equals to 0. Now we have to find what? We have to find the expression of the potential V in this region. Okay, this is our question number 1. And our question number 2 is, what will be the charge density, surface charge density induced in the plates, in these plates, that is sigma, suppose. So what will be the values of the sigma for the plates? Now first we have to calculate this. Then we can easily understand, here you can understand that these are infinitely extended plates, and for this plate, suppose this plate, this is suppose xy plane. Suppose this is a xy plane and this is suppose our z equals to 2 plane. Suppose z equals to 2 plane. That means parallel to xy plane. This plane is also parallel to xy plane. Then this is what? All over the plane, the value of V potential is 0 for this plane, and all over the that means all over for z equals to 0, for z equals to 0, and this is suppose z equals to 2, z equals to 2, for z equals to 0 plane, all over the plane the potential is same. That means when we vary x and y coordinate in the z equals to 0 plane, when we move in this plane in anywhere, in any point in this plane, then the potential is 0. And similarly for this plane, the potential is not varying when we vary x and y coordinate, but the okay, this is clear. But when we vary the z coordinate, that is when we go from here to here, in this path there must be a change in potential. The potential must vary, but we don't know how the potential vary, how the potential, the function of the potential, and that we have to calculate. Now why? Because you can easily understand that here V is equals to 0 and here V is equals to 100 volt. That means here potential will be a function. Okay, so what will be that function? We have to calculate that. So we have only one tool, and that is the Laplace's equation, the solution of the Laplace's equation. Now how we can solve? Now, as we have discussed, here is a symmetry case and the potential is varying only with the z component. Then these two are vanishing here. So we have to carry with only del square v over del x del z square is equals to 0. That means this becomes an 1D case, right? One dimensional case. Now if we calculate this, del v by del z is equal to some constant c and del v over del z, okay, and v is equals to cz plus d, suppose, and another constant. C and d are constants. Now what will be the constants? Putting the boundary conditions, number one boundary condition is z equals to 0. At z equals to 0, the potential is 0. That means at z equals to 0, the potential is 0. Okay, so v is equal to 0 at z equals to 0. That means d is equals to 0. Now at z equal to 2, okay, for your better understanding, I am, suppose this is not 2, this is a variable, suppose d, this is distance d, okay. D, the value of the d you can put from your given question, okay. I am just putting it d constant, okay. Now for v, so v at d, at distance d, at z equals to d, the v is equals to 100. That means 100 divided by d is equal to c, right? So from here I can write that from putting these two conditions, you can easily find that v is equals to 100 over d z. So this is the expression of the potential in the region between these two plates. Now we have to find the sigma. How can you do that? For that we have to use the boundary condition near a surface, electrostatic boundary condition near a surface. What is this? So for understanding that concept, if you have don't concept of that, so I have already made a video, you can also watch that. That was very much helpful for you. So the link of the video I will give also in the description box. Now the boundary condition says us that E above perpendicular, the perpendicular component of electric field above the surface. Suppose I am considering the case of our upper plane, okay. So this is the above region, this is the below region of this plane, this boundary. This plane means this is the boundary plane. Now E perpendicular above minus E perpendicular below is equals to sigma over epsilon naught. Sigma is what? The surface charge density of this plane, sigma, okay. Now we know that E is equals to what? Minus del V del Z. Here, as this is varying with the Z component, so we are considering only Z. Otherwise we have to put this gradient of V, E is equals to minus grad of V. But here, as this becomes an 1D problem, then we have to use only del V over del Z, perpendicular component. So so you can easily understand that E is equals to minus del V over del Z. That means here an additional negative terms will be present. So if we common that negative terms, then this will become above minus del V del Z below, which is equals to minus sigma over epsilon naught, right? You know that the electric field, this means what? The electric field above, right? The electric field above is equals to 0. E above is equals to 0, right? So this term will vanish, and this term we have calculated, and that is this, okay. So we have to derivative it. That means 100 over d with a negative sign here, and this will become sigma over epsilon naught. So this will be cancelled out, and sigma will turn out to be 100 epsilon naught over d. So this is the value of sigma for the upper plane. Now for the lower plane, similarly we can find that. How? Put the boundary condition for this plane. This is the boundary and this is the above region, this is the below region. Then what happens? Then E above minus E below, then you can understand that here E below will become 0. So E above, or I can write E above, okay, E above, okay, E above will be equals to sigma over epsilon naught, sigma dash. I am denoting this density with sigma dash. So this will become E above means we have to derivative it with respect to z. So this will become 100 over d, right? So and negative side also, because E is equals to minus dv dz. So and negative sign 100 over d is equals to sigma dash over epsilon naught. So our sigma dash will become 100 epsilon naught by d with a negative sign. So this is the expressions of the surface charge density on the planes, okay, on the plates, two plates. So I think that you have understand the concept how we can use the Laplace's equation to solve this kind of problems. So later in the next videos I will also discuss the two other coordinate system, spherical and our cylindrical coordinate system. So stay tuned and subscribe and hit the bell icon to get the notifications of my upcoming videos. So take care of yourself. Thanks for watching.